we're going to go over some of Chapter 3 material for the students who have been in quarantine, so it's a hard time keeping up, and we're just going to try to answer some questions and just go over that material. Alright, so I was planning on going through the sections, and then hopefully people have questions as we're going along, or if you have a specific question from somewhere, we can answer that. Okay, so we're going to start off with section 3.1 from our text. And what we're looking for is maximum and min values on a function. So the idea is you have, and this chapter deals a lot with this, you have some sort of function going like this. We are trying to find the peaks and the valleys. So like we're trying to find these values here, which are our highs and our lows. So the lows are called our min, and in particular these are called local min, because they're the min not everywhere maybe, but at least on a certain interval. And then here is this is my local max for this example. Okay, so in general it's not terribly difficult to find these, because if the blue function here is f of x, then I can find these min and max from setting the derivative equal to 0. Because what does the derivative tell me? The derivative tells me the rate of change, or the slope of my tangent lines. So when I have a tangent line that has no slope, which means it's horizontal, I have one of these max or mins. So that's the idea. These points that we call them critical points. And those are the places that make the derivative equal to 0 or undefined. So if you have like a denominator in your derivative, the places where that denominator equals 0 is also a critical point. So we need to consider that as well. Alright, now another thing that we look at a lot in this section is if you trying to find where we increase and decrease. And so if I look at this function a little bit more closely and I start looking at the tangent lines, I mean the tangent lines here kind of look like this. And as I go along, there's the flat one, and then I go up like that. And then these tangent lines start going like this. Does that make sense? Notice that when a line slopes down, if I have a line sloping down, then its slope is negative. Or in other words, if that is a tangent line, that means that the derivative at that point is negative. So all of this area here, right here, my derivative is going to be negative. Why? Because these tangent lines have negative slopes. From this point to here, my tangent lines have positive slopes, which means my derivative is going to be greater than 0. And then I could play the same game here. So here my derivative is negative, and here's my derivative is positive again. So the derivative not only helps me find min and max, it also helps me find where I'm increasing and decreasing. And that would be, we're increasing when the derivative is greater than 0. And when the derivative is less than 0, we say it's decreasing. Okay, now why is that again? Because remember, you always have to remember that the derivative is talking about the slope of my tangent lines. And so if my tangent line has a negative slope, the derivative is negative, which means that my graph is actually going down. Okay, now this, what I covered here, this is actually not in the section 3.1 in the book, but understanding this is kind of the key point of chapter 3. If you get these ideas, the rest of it's pretty simple. Okay, so I'll go over particular what's going on in 3.1, but we need to keep this in mind. In 3.1, we're actually trying to find not just min and max, but we're trying to find absolute min and max. Okay, so now what absolute min and max are, these are not just local min or local max, these are definitely the high points and the low points. So right here, that's a local min. Okay, now again, that comes from a critical point. Now what's different about this section from the others is that I'm going to consider just on a closed interval. So I could have a graph. So here A to B, we're going to just be on a closed interval. Okay, so we're not considering positive and negative infinity. I might have something like this, for example. Okay, now if I'm just looking at local min, here I have a local min, or a local max, a local min, a local max there. But if I look at the whole thing, so local, you got to think this is like the highest mountain in my state. The highest mountain in my state is a local max, but more than likely it's not the highest point in the world. So it's not an absolute max, it's just one relative to where I am. Kind of the little fish in a or a big fish in a little pond idea. Okay, so for this graph in particular, look, my absolute min will be this endpoint. Even though this is a local min, I have a point less than that. My absolute max will not be the endpoint, it'll be this critical point right here, because that was definitely the highest point on this interval. Okay, so what we can say then is we can take, let me find an example. This is actually example 8 from the textbook. And you have a function, it's a cubic function, x cubed minus 3x squared plus 1, and we're limiting ourselves from -1/2 to 4, okay? So I'm trying to find absolute min and max. Well, let's try to figure out how, what are the candidates for absolute min and max. So if I go back to this picture here, notice that my candidates were either the critical points, which are these 3 places, or the endpoints. Okay, so the candidates for these absolute extrema are the critical points or your endpoints. And those are the things that we need to test. Alright, so for example 8 then, what I'm going to do is first find my critical points, and then I'm going to just, all I have to do is test the critical points and the endpoints to see which one gives me min and max. Alright, so first of all, my critical points here, we find the derivative. Now, you gotta know your derivative laws. If you're having a hard time with the derivative part, you know, conceptually, chapter 3 is not too difficult, but you still have to have that ability to, you know, do product rule, power rule, quotient rule, chain rule, etc. If you need help with that, you know, I'll be happy to help go over that stuff as well. Alright, so my derivative here is 3x squared minus 6x, and I'm going to set that equal to 0 because I'm trying to find my critical points. Thankfully this one can factor, so I take out 3x, and I'm left with 3x times x minus 2. So I get my critical points then to be 0 and 2 from my factored version of my derivative. Alright, so now I have, again, my candidates are what? The critical points, I have those, and the endpoints, I have those as well. That's the -1/2 and the 4. So to find the absolute min and max for this question, all I have to do is test those points. So test f of 0. Well, let's do it in order. Let me try this again. F of -1/2, f of 0, f of 2, and f of 4. So those are the points I test. Alright, so I just test these out into my original function, not the derivative, right? Because the derivative's not telling me actually how high up and down they are. The original function does. So, you know, this is just a simple algebra thing. You have -1/2 cubed minus 3 times 1/2 squared plus 1. And I'm just going to kind of cheat a little bit because we can just evaluate those pretty simply. That's 1/8. You get 1 when you plug in 0. You get -3 when you plug in 2, and you get 17 when you plug in 4. Alright, so now all I have to do is just look at those and see which one is the highest and which one's the lowest. So there's my lowest, so there's my absolute min, and there's my highest, there's my absolute max. So one of the extreme points came from a critical point, the other one came from an endpoint. And I like to, I mean, you know that I like to summarize things with a sentence, so we could say that the function f of x has a, not local, an absolute min at the point 2, -3, and an absolute max at the point 4, 17. There's my high and low. if we're going to graph this function, it would look something like this. Let's see, so we're just going from -1/2 and we hit 1/8, so we're very low. At 0 we hit 1, so up here. At 2 we hit -3, and at 4 we hit 17. And if you're just going to draw it, it's polynomial, so it's smooth. It's going to do something kind of like this. Alright, so then when I see this, I can see obviously here's my min, my absolute min, and here's my absolute max. So at 0 here, we do have a local max. So that's like a max, you know, that's the highest point in the region, but it's not the highest point overall. It's not the highest point over everything. The highest point over everything would be 417. Now, we have to limit ourselves from -1/2 to 4 or over some closed range to guarantee that we would have an absolute min and max, because it's very possible that if I just graph this thing from -infinity to +infinity, it's going to do something like this. And so at that point, the best you can do is absolute min and local min and max. You won't have any absolute min and max. Does that make sense? Okay, so for 3.1, we mainly just stay with a closed range. There are situations though where you could have a graph that has an absolute min and max, but you don't really have to limit your range. So if you had like asymptotes or something like this, vertical asymptotes, you might have a function that does something like this. So at this point, I could have, let's say this is -a and this is +a. I can't test the endpoints -a and +a because I have these asymptotes. So I'm going off to infinity as I'm getting closer to -a and a from the appropriate directions, but I still have an absolute min in the middle. Right, so it doesn't have to be a closed range necessarily. There's an absolute min right there. I would just find that how from the critical point, right? Or, I mean, even think about just a normal parabola. You just take a good old-fashioned parabola from college algebra. I'll have a local min. I mean, not only a local min, I'll have an absolute min at the vertex. Okay, so there, the critical point will be the absolute min. But the only time I can guarantee you that you'll have absolute min and max is when we limit ourselves onto a closed domain. And so that's kind of where we start with this. And you'll notice almost all your homework questions, that's what they do. They give you a closed domain, ask find absolute min and max. Is that good? It's not as tricky as we kind of make it out to be, honestly. All it is just taking the derivative, plugging in your two endpoints and your two critical points, or however many critical points you have, and then just seeing which one's the biggest and which one's the smallest. So, but I think it leads back to the original discussion we had here of trying to figure out increase and decrease. Let's see, we took the derivative right here of this function. Here's my derivative. That's a parabola. And let's see, if I graph that parabola, let me graph it real quick. I'll try to graph it right here. Let's see, that parabola has a 0 at 0 and another 0 at 2. And then it's going to do something like this. So that's my f prime. That's a rough sketch of f prime. Okay? Look at the relationship between these two graphs here. And we are limiting ourselves again to -1/2. So I'll just cut it off right there. And 4 the other direction, something like this. So my parabola looks something like that, okay? From -1/2 to 0, so from here to here, the derivative is positive. It's above the x-axis. Between 0 and 2, my derivative is below the x-axis, right? It's negative. And then after that, I am positive again. Okay? So here, my derivative, I'm thinking positive or negative, above or below the x-axis. Now, what that translates to in the original function is, notice that from -1/2 to 0, my derivative was positive, what is my function doing? From -1/2 to 0, it's going up. It's increasing. And then from 0 to 2, it's decreasing. It's going down. And then from 2 onward, or we limited ourselves to 4, I'm going up again. I'm increasing. So when the derivative was above the x-axis, my original function was going up. And when my derivative was below the x-axis, my original function was decreasing. That's a hard shift to make for us, because what a lot of times we look at the derivative and we go, well, the derivative is decreasing. That's not what I'm asking here. I'm not asking for the derivative to be increasing or decreasing. I'm asking for the derivative to be positive or negative, above or below. When the derivative is above, the original function is going up. When the derivative is below, the original function is going down. Is that good? Does that make sense? Let's go to 3.3. And 3.3 talks about a lot of this. And this is how derivatives affect the graphs. Okay, so derivatives and graphs. And I will let you know, I do have some YouTube videos going over most of this material. So I think that might be a good resource for you as well to kind of look over. I mean, I'm just basically kind of explaining the same stuff I am now. But let's do this example. So this example 1 from the book, it says find where the function f of x, that is 3x to the fourth minus 4x cubed minus 12x squared plus 5 is increasing or decreasing. Okay? Alright, so what we're trying to do is figure out where it goes up and where it goes down. Now, if they asked me to find, hey, what's the local min and the local max, I would instantly know to go to the derivative. Well, actually, going up and down also relates to the derivative. And that's what I was trying to point out earlier. Okay, so what we're going to do first is find the derivative. And this derivative is not too bad. We get 12x cubed minus 12x squared minus 24x plus 0. Okay, so there's its derivative. Now, if I graph these two things together, I could see a relationship between the two. What I want to do first of all, though, is find my critical points. So again, that's going to let my derivative be 0. Oops, we don't plug 0 into the derivative here. We're just trying to solve this derivative for 0. And I'm going to go ahead and factor, because notice I can take out a 12x. And when I do that, I have x squared minus x plus 2 equals 0. Okay, so I think I can factor that quadratic as well. Two things that multiply give me 2, add to give me -1. Am I thinking of this right? Yeah, how about -2? Oh, that's a -2. Okay, good. I was thinking, what's going on here? So I think that's correct. X squared, yes. Okay, so I have 3 critical points then. I get 0, -1, and 2. Those are my 3 critical points. So I know on my graph, on my original graph, that at these points, let's see, here's -1, here's 0, and at 2, I'm probably going to have some sort of min and max thing going on. I don't know exactly what's going on there, but we're going to figure it out. And now, to figure out increase, decrease, what I need to do is look at the derivative. And all I care about is whether the derivative is positive or negative in between these areas. Okay, so I'm kind of talking over myself. What I know is that the derivative is 0 at these 3 locations. Okay, so the derivative hits 0 there. What's it doing everywhere else? So I'm going to pick some test points. For example, I could pick -100, something less than -1. How about -1/2, something between -1 and 0. 1, and how about 50? So I'm just plugging in things to test positive or negative, and I'm just looking at the derivative to do that. Okay, so all I care about again is the derivative positive or negative. Now, a quick way to do this is let's put our factored version of our derivative here. And let's put my test points here. And again, I only care about positive or negative. So for example, when I plug in negative 100, that times 12 is negative. That minus 2 is negative, and that plus 1 is negative. When I have three negatives multiplied together, I end up with negative. That tells me that every value less than negative 1 will make my derivative a negative. I don't care what the actual number is at negative 100. I just need positive or negative. Okay. I do the same thing with negative 1/2. So negative 1/2 times 12 is negative. Minus 2 is negative, but negative 1/2 plus 1 is actually positive. So now when I multiply these together, two negatives cancel out, I end up with a positive here. So I got positive between negative 1 and 0. I do the same for the other two. For 1, I get positive, negative, positive. So that results in a negative because I only have an odd number of negatives. And then when I plug in 50, I think I get all positives. So that makes all of that positive. Okay, this is what in algebra we call a sign chart. And what we actually solved was a polynomial inequality. And by the way, if you need help with this, I do have a video going over polynomial inequalities for algebra. Okay, but now let's interpret this in a calculus sense. So when my derivative is negative, that means that the rate of change or the slopes of the tangent lines at those locations are negative. That means that my function is actually going down. So this interval here is the area of decrease. Between negative 1 and 0, I'm increasing again. From 0 to 2, it's going down again. And from 2 onward, I'm increasing. So to summarize, we can say f is increasing on the intervals negative 1 to 0 and 2 to infinity. And we're decreasing on negative infinity to negative 1 and 0 to 2. Okay, does that make sense, at least from the algebra standpoint of what we did there? Alright, so let's graph the derivative, actually. It's going to go hit 0 here, here, and here. I was negative, positive, but I got to hit 0 again here. Negative again, and positive. Alright, so there's my derivative. Is that good? Again, we were negative through here. We hit 0, then we went positive, then we went negative again, and then we went positive again. So what I know about my original function, okay, so there's my f of x. Alright, so I graphed it on top. Now look, from here to here, f of x is doing what? It's decreasing. From here to here, between my min and my max, f of x is increasing again. Between here and for 0 and 2, I'm going down again, and then after 2, I'm going up. Do we see that? Down, up, down, up. And look how that relates to the derivative. When the derivative is negative, my graph is going down at those two places. When the derivative is positive, it's going up, just like that. Does that make sense? Okay, so with this, we have one more thing we can add to it, and that's called the first derivative test. And I think it makes sense. So what we're saying is, let's let C be a critical point, and F be continuous. All right, so that we've kind of assumed that we're dealing with continuous functions for the most part. We don't want asymptotes. We want jumps like that. That kind of messes us up. Here's what we can say: if f prime is negative before c and positive after C, then f has a local, well, let's think about it at C. Okay, let's think about what we're saying here. The derivative, we said we're going from negative and then it switches to positive. All right, so what does that say about the original graph? If it's negative, what does that say about f? It says it's decreasing, right? If it's positive, that means we're going up. And C is a critical point. So that means at C, that's when we have a horizontal tangent line. So if my derivative is going from negative to positive, that means the original function is going down and then up. This has to be a local, what? A local min. If I am switching from negative to positive, I have a local min. Does that make sense? And I could say the same thing, I could flip it around. If I switch from positive to negative, then what happens? That means I went from up, hit my critical point, down, I have a local max at that point. And that's what we say, that's what the first derivative test is. Okay, so if I go back to the question we just went over, look at my sign chart here. I went decrease, increase, decrease, increase. I know, so let me say from previous example, we have f of x has local min at, let's see, where are our local min? That would be where I switch from negative to positive in my derivative. So, all right, so we have a local min at, what do we say, at x equals 0 and x equals 2. And then we have a local max at the other critical point, which was, oh, I'm sorry, our local min is at x equals -1 and 2, and our local max is at x equals 0. Does that make sense? And this is from the first derivative test. It tells me that. Okay, now let's look at the graph. Is that consistent? Look at my graph here, the yellow. I'll trace it in red again. So this guy, look, we have local min at -1 and 2, and we have a local max at 0. That's exactly what we just said. Sybil, is this answering some questions? Good. The big part here is when you're looking at the graph, let's see, didn't we have, yeah, up here again, is being able to switch from the derivative to the function. And again, when the derivative is positive, that means my original function was going up. And when my derivative was negative, the original function was going down. And just drawing the connection between these two is very helpful, very helpful. And I have videos going over all of this stuff. All right, great. Why don't we pause there, and next time we can go over 3.2 and some of the other stuff. Does that sound good?